this. And in your book, on page 78, you'll see this picture that has a whole bunch of different angles on it. And if you look at the angle that gives you the longest range downfield, you'll get the answer number 1, which is 45 degrees. Feel free to stop this at any time if I'm going too fast. If you also look at the angles, you'll notice that in that book that a 30 and a 60 degree angle give you the same range. A 15 and a 75 degree angle give you the range. So any angles that add up to 90, sum is 90, give you the same range. And so therefore on this next one, if I have a 32 degree angle, well 32 and 58 give you 90. So a 58 and a 32 degree angle would give you the same range as well. The next question says, what angle below the horizontal ground would give the ball the same velocity as the 50 degree angle shot above the ground? So if I have a little, cliff here, and I shoot a ball up at, let's say 50 degrees here, and let's just say this is going 100 miles an hour. I'm going to extend my horizontal out like this. Well, what goes up must come down. So therefore, it's going to come down at a 50 degree angle as well at 100 miles an hour. And since opposite interior angles are the same, that means this is the 50 degree angle, and it's still going 100 miles an hour here. So if I come over here to the other side, I could shoot a bullet down at 50, and it's going to come out of the gun at 100 miles an hour. And this green is the same as, so the green right here is the same as the blue right here. So once again, if you shoot a ball up at 50 degrees, it's the same, it's going to land at the same speed as if you shot it down at 50 degrees, because gravity is going to slow that ball down on the way up, but it's also going to speed it back up on the way back down. So it accelerates back to the same speed it was when it came out of the gun. If you go to the next one here, if I shoot a bullet and drop a bullet from the same height off the ground, they will both land at the same time. So the one's just going to land about a mile away, but they both land at the same time. Gravity doesn't go on vacation just because you shoot something. So gravity pulls both of them equally in the vertical direction. Number 3, sort of the same thing as actually it's number 3 twice. A bullet shot upward at 60 degrees, another shot down. Which one hits the ground first? We'll use common sense for this. So if you go back up to the first number 3, which I sort of skipped around, so we're going to come back up to this. The one that's going to hit the ground first is the green one here, because it has less distance to go. Okay? Now, which one will hit the ground at a greater speed? Once again, they both hit at the same speed because gravity slows the ball down that's shot up and then accelerates it back to the original speed. So again, feel free to stop at any time because I know I'm going way faster than you can write. Number 4, it says a ball thrown at 30 miles per hour at 60 degree angle going straight up. And now I want you to look at page 77 of your book, because it's going to give you a bunch of different diagrams here about a projectile that goes up like this, and it comes back down. Boy, that's a good parameter. And so this is now 30 miles per hour. That little arrow right there, vector is 30. And this angle right here is 60. And it says, what is the direction of the acceleration at the beginning of the throw? Well, even though it looks like you would put down 30 miles per hour at 60 degrees above the horizon, that's not the direction of the acceleration. The only force that's on here, the only force on a projectile is gravity. And which way does gravity act? It always acts down. So your answer to number 1 is down, because gravity is the only force on it. Now, what's the direction of the velocity? Well, that's different. The velocity is actually what you see in the picture. So you see that this vector, which is your velocity vector, is 30 miles per hour. So it's 60 degrees above the horizon. Let's go to number C. It's a tricky question again. What is the acceleration, both magnitude and direction, at the top of the parabola? Well, at the top, Then you have going like this, and you have another bridge going like this, and another bridge keep going like this. At the top of the parabola, the direction of the acceleration you would think would be to the right. Well, that red line is not the acceleration, that's the velocity. Remember, the only thing that makes the thing accelerate is gravity. So therefore, which way is gravity? It's down, and it's always at 9.8. Part D is what I was just talking about. What's the horizontal acceleration during the throw? Well, if you notice all of these red lines, in your book especially, if you look at that, the red lines are all the same length. If you look at the green lines here, it starts out the green line's really big and then it gets a little smaller. Up here at the top, it's not even existent. And then down here, the green line starts getting a little bit bigger, and down here it gets a real big. So that's because gravity is slowing the ball up as it goes up. And so the green lines get smaller because the velocity is going down. As they come down the other way, the green lines get bigger because it's speeding up. But the red lines are always the same length because there is no horizontal acceleration as long as there's no air. So the answer to part D is 0. What's the direction of the velocity at the top of the throw? Well, the only velocity you have is that red arrow right up here, and it's going to the right or horizontal, east, however you want to say it. Part 50, what's the resultant velocity of the ball at the end of the throw? Well, once again, what goes up must come down. So therefore, if it went up at 30 miles an hour, it's got to come back down at 30 miles an hour at the same angle, which is 60 degrees. And the next part gets you a little bit trickier here. What's the velocity at the top of the parabola? Well, a lot of people want to say 0 because gravity would have slowed it down to 0. But that's not the case. Each one of these red lines is the same length. So you see how this red line here is the adjacent side, the green line is the opposite side, and the 30 miles an hour line is the hypotenuse? Well, since I know the hypotenuse and I'm trying to find the adjacent side, what you have to use here is the formula for cosine. So cosine equals adjacent over hypotenuse. If you cover up to A to find this adjacent side right here, that adjacent side is cosine of the angle, so the cosine is 60 times 30, which gives you 15 miles an hour. So since there's no horizontal acceleration, this is always 15 miles an hour along the whole trip. It's 15 here, 15 here, it's 15 going sideways all the time. In part 5, you got a gun that fires a projectile 100 meters per second, and you have to prove mathematically that a 40-degree angle and a 50-degree angle give you the same range. Well, now you have this weird looking formula here. It's really big. I put dx because when we talk about range, if you're going to shoot something downrange or downfield, that's the distance in the x direction. So I got distance in the x direction equals r, which stands for range. And that equals the velocity squared sine of 2 theta. And 2 theta is in parentheses there, so make sure you put it in parentheses, divided by g. So now what I'm going to do is put in the 40-degree angle and do a problem for that. So I'll put in the 40 degrees for theta, put in the 9.8 for gravity, and I get 1,004. Then I do another problem the exact same way, but I'm going to put in a 50. So if you notice in one problem, I'll put in the 40 up here, and then the other side I'll put in the 50, and both give you 1,004 meters. So two angles that add up to 90 degrees will always give you the same range. And it makes no difference what speed they go at, as long as you have the same speed for both of them. Come down to the next one. This is what I call the shoot the monkey demonstration, and in class we'll actually take a blowgun and actually shoot a tin can falling from the ceiling. But it says if a blowgun is aimed toward a tree and the coconut falls at the same time the blow dart is fired, explain where the shooter has to aim the dart. Well, you're going to aim the dart directly at the coconut, and let's see if I can draw this out a little bit here. And say that this is my gun right here. Here's my little bow gun with the dart in it. And here's going to be my coconut up here. Now, if there was no gravity, the dart would come right at the coconut. And so I'm going to call this my zero gravity path. Zero G path. So if there's no gravity, the dart goes straight, the coconut just floats. Okay? So aim the dart at the coconut, because without gravity, the coconut would not fall and the dart would shoot into a straight zero gravity path. But with gravity, here's what happens. With gravity, the coconut starts to fall. And so now the coconut ends up right there. But the dart falls the same amount as the coconut does. So the dart's going to come out of the gun. And if the coconut fell 1 meter, the dart's also going to fall 1 meter because gravity acts the same on both. And so it's falling, though, from the zero gravity path. So this would all be 1 meter for both of them. And so as long as you aim it at the coconut, you will always hit it. Now, the poor AP kids have to prove this mathematically. And so if I want to prove that the height of the dart, and remember I'm going to call the height the distance in the y direction, I'm going to start off with one side being the dart, and I have to prove that that's going to equal the height of the coconut. And so I'm assuming that it's going to be because they got to hit each other. Well, in your equations, the kinematic equations from last chapter, we talked about a formula that said the distance, and I'm going to do everything in the y direction here, equals the distance original plus VOT plus 1/2 AT squared. And if I'm going to assume that they're going to be equal, this has to be the same thing over here, that the distance in the y direction has to be the original distance plus VOT plus 1/2 AT squared. Okay. Well, let me just make this formula a lot simpler. If we're going to assume that these things are equal, so they're going to hit, I can cancel this out because gravity is going to be the same on both sides. They would have to hit at the same time. So we're going to assume that. So that means that this and this both cancel out because gravity and time have to be both the same on each side of the equation. Okay. I can also cancel out the distance in the y direction part over here. Okay. And this distance in the y direction, since we're assuming they're going to be equal. But now I got to prove that they're going to be equal. So let's look at the, actually let's write that down. So the 0.5 AT squared cancels. And I got left with that equation over here. And it looks like this is going to freeze up on me. I'm hoping I might have to make another video because it looks like it's freezing up. Let me see if I can get this to stop.